So I'm going to try to do a couple things in the discussion today, but I'm very pleased to be here. It's been really about 2 years since the last time we talked about blue waters in detail, at least I did at your meetings. So I'd like to bring a little bit of an update and a refresher for blue waters, particularly for some folks that have not heard anything before in detail. Talk, as Merle said, a little bit about sustained performance that you may have heard of and me talk a little bit about before. And then I'd like to imagine what would have happened if we had done a different blue waters. And then one of the really important things is the updates of the science teams and how they're being able to make use of the system to do things that can't be done elsewhere. And a little bit about what we're learning about the future and future generation problems. So hopefully we can go through that. And I'll go first in the refresher. And they'll be in the slide content as well. So a couple reminders. The goals that we had for blue waters are here. Sustaining more than 1 petaflops on a broad range of applications. You've heard that a number of times. Full advantage of being able to use this system. We put an awful lot of effort in the last 2 years, actually 5 years, of helping teams make full use to the maximum extent that they can. Enhancing our ability to operate and sustain blue waters. We have the most instrumented system in the world, I believe, for anything of this scale. About 8 billion data points a day flow into our analysis and monitoring systems, and we're now making use of that. It took us about a year to get to the point where we could accumulate all that data and still handle it. So now we're reaping the benefit of being able to start to analyze that data. So that's a big data problem in its own right. And then the environment that goes around blue waters, not just the single machine, and being able to be innovative and bring innovation to science, engineering, and industrial communities. If we go back again to the original requirements, maximum core performance, low latency bandwidth, fast memories, large I/O and data archives, and reliable operations. This is what NSF requested of the machine that became blue waters, and that's what we're providing. But these two slides are important to set the background as we go forward in a couple of discussions. So we have a machine and an ecosystem. It's actually a system of subsystems, the biggest one being the computational analysis system, 40% or more larger than any system Cray had ever built and has ever built in their entire history as a company. Much larger than anything else, much larger interconnect. So sustained performance, large memory, large amounts of storage, production, and a transition into the future. A little more detail on the schematic. Is this, let's see. Can I use this to point?
There's a button on the side.
On the side, okay.
No, it's a switch needs to turn on. Other side.
Other side. Yeah. All right. So the main computational engine for blue waters, an analysis engine, 288 racks of compute nodes, about 27,000 compute nodes in their own right. Cooling infrastructure, all liquid cooled, and then we have several interconnects, large parallel storage space based on luster, the offline, nearline storage space, and then a wide area network going out to the rest of the world as well as attaching to or connecting to all the other systems there. A more detailed view of this is we have two types of nodes on blue waters, XE nodes, that's all x86 AMD interlogos processors, but all x86 instruction set with 4 gigabytes per floating point core. You can see the core numbers. We talk about everything in nodes because we don't really distinguish what a type of node is. People can use the nodes interchangeably. We also don't know really how to distinguish, at least on this type of technology, really what a core is compared to other people's cores. So we talk mostly about nodes, but here's translations of that. And XK nodes, these are the nodes that have one socket filled with x86 CPUs and one socket filled with NVIDIA K 20x GPUs. So this is a balance of a system. I'll talk a little bit more how we got to this balance and a little bit more about how it's being used. And then a variety of service nodes, one of the largest Lustre configurations with almost 600 LNet I/O servers, and then they connect over InfiniBand fabric to the disks. They connect over the 40 gig fabric into the servers. There's about 100 servers in this list of things people use to access and move data around the system and then out to the wide area network. 4 different interconnects in here, the wide area network, the 40 gig network between subsystems, the Cray Gemini high-speed network that's inside the machine. That's the heart of how we can do parallel computing, and then other networks as well as an InfiniBand network to connect to storage. So a complex set of systems that pull together and allow people to do very integrative, very complex tasks. Most of our activities are multi-physics, multi-scale activities across a wide range of science. So we're proud of what we've been able to accomplish. 2 or 3 weeks ago, we had our 2nd anniversary, but these are just some hints of what the PIs and the science team leaders are saying about this, and I'll show you some other ones in a little bit. But to whet your appetite, the first ever supercell produced in a long track tornado, the entire length and time of the tornadoes that came about in Oklahoma about a couple years ago, that was simulated for the first time ever. What takes normally months now takes weeks. And that is not just Tom, but that's a number of the other teams. In some cases, we've been able to reduce what takes months into hours for some of the workflows that we have. And I'll show you an example or two for that. New results, fundamentally different than what was thought of before, going from 2D to 3D, or going from asymmetrical to full dimension. So what appears to happen in studying only part of a system, like an exploding star, didn't reveal what happens if you study or simulate the entire star. Just the amount of computing and the time it takes for a solution. And Blue Waters is credited here with a whole new type of molecular dynamics simulation in the software that is used for that. So a year ago, we came out with our first annual report based on our symposia, and the reports from the science teams. This had about 58 different science teams reporting what they were able to accomplish, and also a little bit about what they wanted to do before. If you were on the mailing list for PSP last summer, if you remember, or on the mailing list, you should have gotten one of these reports. We mailed it out to about 1,000 people. But if you weren't, there's some in the back if you want to look through all the other things that we don't have time to talk about today. And we'll come out with another one of these about the end of the summer. We have our symposium going on next week. Last week we were in parallel with you, so this week we're doing it the week after the PSP meeting. If we look at the usage of the system, and this is by usage and science discipline, this for a year ago, we do our annual reports in July, so this is out of the first annual report. A year ago, our distribution looked like this. It changes because we don't choose what projects get on the system, and others do that for us. But about 25% was biophysics and biology and biomedicine. About 20% was astronomy and astrophysics, and nuclear and particle physics is about 25%. 10% is climate and atmospheric sciences, and then you see chemistry, computer science, engineering, earth sciences, physics, flow dynamics, a variety of other things, and that now has expanded. These categories have expanded as well there. We have social science, economics is one of the projects. An economist, a Nobel laureate economist, is running an economics project, as well as some other things like social networking projects that are there. Our demographics, as of today actually, we are currently serving about 144 projects or teams The teams sometimes are small numbers of people. Sometimes they're 30, 40, 50 members of the teams. We have, through the National Science Foundation, that has 80% or more of the resource. They allocate 80% or more of the resource. About 30 projects. We call those and some others major projects. Those get enhanced services. And those are the ones, if you figure 80% of Blue Waters divided by 30, they get a large amount of allocation for each project. And overall, we've served over the last 2 years 37. 7 of those have finished their work and go on, because these are not continuing projects. Every project has to define a science goal. They have to define the resources and the methods that they'll attack the science goal with. And when that science goal is achieved, then they go off. They may repropose a different science goal. That's perfectly fine, but they may not, and they may be off doing other things, or other teams come on. So we have a rotation of about half the teams over this time period have been new. The other half have continued working on the system. So about half are new every year, and we're just waiting for the next announcement for the teams from NSF. Our GLCPC, that's a collaboration of essentially the Big 10 schools along with others. They do about 10 projects a year. It's very large for those schools, modest in the size of what we have on the major teams, and about 21 so far. Illinois has a variety of allocations. We have 16 Blue Waters professors. They get a yearly allocation along with the title Blue Waters professors, so it's a good way to recruit people or retain people, as well as those are probably the premier computationalists and analytics faculty here at U of I, so they have access and they have discretion on how they use that access. But we also have general projects at Illinois. These are relatively large. The minimum size of one of these projects is probably 1 million node hours. Roughly, you can multiply by 32 if you want to translate to core hours. The largest size is about 20 million node hours a year for multiple years for that. These range more or less from 100,000 node hours to 1 million node hours for that. Still extremely large for what an individual institution would have available for that. So about 1% of Blue Waters is about how much computing NCSA has had in its history before Blue Waters. Innovation allocation for general things, and also we have programs that will help teams improve their application code and work with experts in the field outside of Illinois and outside of the Blue Waters project to bring new technologies and new methods to bear on how you solve I/O bottlenecks, how you solve scaling bottlenecks, how you solve bottlenecks within just the individual CPUs, or how you improve your resiliency or your topology awareness. And then the industrial projects, we've had 8 throughout the distance, and I'm not going to talk about those in detail because you've heard about some of those as well. And then a lot of educational activities as well. About half, this is the distribution of who is using the system, and about a little less than 25% are faculty. A little less than 20% are postdocs, and close to 40% are graduate students. So the fact is that we're just by access and just by use of the system, there's a large cadre now of people that are going early in their career using such a resource that they have access to that's unprecedented. And then you can see some of the other categories as well. Another aspect is where are these people coming from? So this is a map not of all the people using the system, but only of the institutions that are associated with the principal investigator. And you can see that the actual usage spans a good amount of the United States, about 38 states, I think. 76% of the states have people from those states using Blue Waters. If we count numbers of researchers, partners, then it'll actually go up a little bit. And a number of these states, about 15 of those are F-score states or states that represent some economic challenges as well. So a wide range of people are using the system. They're not all in one place, and that's how our service models are created. So this is moving a little bit into some usage demographics. This is a good day on Blue Waters. This is a map. If you go to our portal, you'll see this, this rotating torus. It rotates around. Each dot is a Gemini network interface, and that represents 2 nodes out of the 27,000 nodes or so. This is a good day. Where about 99% of those nodes were in use by science applications. And they're packed very well. So this represents the 10 biggest ones. If we showed all the jobs, it would be way too noisy. But on the portal, you can see the 10 biggest ones. This is not a day that is absolutely like every day. We're probably more like in the 85 to 90% range. But that's still, by running jobs of this size, where the smallest job here, I think, is 4,000 nodes, 128,000 core equivalents, is the larger jobs here. It's a pretty good representation of the big things going on Blue Waters. Last year, by amount of time used, the median job size was about 64,000 core equivalents, 2,000 nodes. So that's about 1/10 of the entire system. That's the median size. That's much larger than most other systems exist, and that just happens to be where the sweet spot is. This would range based on what quarter and what teams are using that, because having a relatively small number of teams, 150, that are very large in their usage, some teams go on campaigns and they change, so we see some change of that. But I've never seen it below, say, 1,200 nodes is that median in any of the reports we've done. Sometimes it's above that. If we look at the XK region, 4,200 nodes. It's also the median use of that region is about 400 nodes, and that's also about 10%. So that's the type of parallelism people are extracting, and they're doing parallelism in the accelerated space as well as in the traditional x86 space of using systems. Another thing that is a characteristic of the people using our systems is this is the distribution of time from 1 hour to 24-hour run times. 24 hours is our maximum standard runtime. Anybody can ask for a 24-hour run through a standard submission. If you want more than that, you have to ask for a little special consideration. We do that quite a bit. But if we look at that, the large majority of time is in the 24-hour space, 23-hour space. So long-running jobs is another characteristic of Blue Waters. That makes it efficient for us, because once we give somebody the nodes, it's going to run for a long time. But also that means that there's far less startup and overhead of restarting applications and jobs as they run. And this is another view that kind of combines those two things, the large-scale jobs and the long-running jobs. So this is from a tool that we use to accumulate some of the usage data, but also Exceed. The Exceed project uses the same tool. This is Blue Waters, about 500 million. This is core hours, really, the equivalent, in the average job size. And if we go look at the similar data in the Exceed space, it's about 28 core hours. So different profiles, different sets of people using they're not meant to be the same thing, but it is, both are serving their communities very well, range of communities. There's some overlap, but also a variety of things that are not. So that's some of the things that distinguish what we do on Blue Waters and what types of customers and clients and projects we're serving. We also do serve ones that are not highly parallel. That's fine. Some of those are doing unique things because of what they do. Many of those have different phases in their usage. So there are some teams, I think there's 1 or 2 in the room, that have to run very, very large parallel applications, but then also to analyze or understand what they're doing. They also run a number of individual node runs for visualization or analysis. So we have this mix. Not everything has to be highly parallel, but there has to be a good reason for using such a resource in an efficient manner. This is some data, because we always are asked about how did you decide the mix of GPUs versus CPUs. So we talked to the science teams when we were putting the system architecture together, and we had about 18 teams that were already identified as using the system or allocated on the system. And we talked to them and tried to find out how many teams were ready to use GPUs, how many teams might be thinking about using GPUs, and how many teams thought that they could do that for their production science. So we chose the ratio, which is about 16-17%. And now this is from the first about year and a half up through December of the usage of all the teams out of the 140 teams that, or almost 200 teams that have used Blue Waters. These are the teams that had any time using a GPU. It could have been a second on a GPU, but these are the teams that have that time. And then the teams, the blue lines are how much node time, node hours they used on the GPUs and how many node hours they used in the x86 space. So what you can see, what we had identified is there were several teams that were really, really ready to use GPUs in production science. Jim and John from NAMD was one of those teams. The QCD collaboration, two other molecular dynamics codes, they had converted very early in the move to GPUs. They were ready to do it for the production science. There were a few other teams wanting to try things out. But in this case, this was the number of activities that we saw our teams using the GPUs. That's increased a little bit from the time this chart was put together because the team doing seismic research for the first time is using GPUs heavily in a phase of their analysis that just started up their next campaign, their third campaign on Blue Waters. There's another example I'll point out where that team is working to convert to use GPUs, but they're not there yet. So, while we have a modest number of applications that are using this on a very regular basis at very high allocations, it represents a relatively small number of the application suite that we see available, right? So on average, those teams, particularly those major teams, use 2 or 3 codes. So you can think that we probably have 100 or 140 major applications somehow running on the system. So this is the representation of the readiness. Our job is to take a lot of these teams and other teams and get them able to use the GPUs very efficiently and help migrate their codes along with our partners like Win-Mei Hu over in computer engineering and NVIDIA and Cray to help make it easier for them to move to get the efficiencies of many cores. So that's why we think of this as a transition system going into the future, so teams can migrate their codes while still doing their production science and move forward rather than being limited in what they can do by either all of one type of node or all of another type of node. So we're going to switch topics a little bit. So that's Blue Waters. That's what we've been doing. We're all happy to talk to you about that. You've heard some things. Evan talked a little bit about some of the things going on Blue Waters as well as iForge. So. But as Merle said, we had a couple conversations, and he asked me to talk a little bit about sustained performance and also this idea of balanced systems, because we're very proud of the balance that Blue Waters has in it, and I'll try to highlight some things that we think are enabled by that balance that are not just flop-rated systems. So we talk about sustained performance. That's always been our mission. You saw that from the very original requirements of Blue Waters. Didn't mention at all anything about a particular rate of processing. And to us, that means getting the work out of the system as quickly as we can. Effective work, real work, not just funny work or overhead work, and time to solution. So we have our benchmark suite. I won't go into a great deal of information about that. I'll show you a slide or two. We call it the SPP. But one of the motivations and one of the things that we decided very explicitly to do is not list our system on the top 500 list. Why is that? Because we all know that it's not necessarily the best measure for what real work is. So that worked out pretty well. We're still one of the few large systems that publicly decided not to list. Some systems are hidden, some systems don't acknowledge that they exist, but of the systems that are very publicly available, we're one of the few systems that made that decision and publicly justified that. So that was one of our motivations. Our SSP tests and you may have seen a slide or some of this before, so this is a refresher, consists of 12 codes here. The scale that we ran those codes at, so the actual test did not run full system test in this regard to come up with the SSP measure, and then there were 4 codes that ran different problem sets on the XK nodes, and we put those together and came out with our estimate through a very solid methodology of what the sustained performance is. At least 3 of these codes and 3 of these codes ran at the full system size in the XK region across the XE region, and we had at least 3 other codes that ran, or 4 other codes that ran at the full system size, all the nodes for extended period of time as part of our testing. The coverage, again, of this test shows a display of application areas, science disciplines, but also of methodologies that were important to us. So we think it's a fair representation of the workload of the machine. We have actually now seen that as we we're able to measure the actual performance of many of our codes that are running on the system. Yeah, there are a number of codes that report above a petaflop of performance for their science applications, their real world applications. So we think it's a pretty correlated measure for that. By this measure, comparing to a blue water system to a system that came, same interconnect technology, same vendor, came in the same time period as blue waters. We were actually installing the system simultaneously. While some of the characteristics are different in terms of peak performance or whatever, by the SSP, Blue Waters has a higher SSP, almost double, or a little more than double than what Titan has because of the choices that they made in architecture. So that's pretty cool. It's based on our workload. That number is perfectly good for the DOE workload, the workload that Titan's serving, but for the NSF workload, the industrial workload that we are supporting here, this is what we think is the real sustained performance of those systems. So I wanted to spend a slide or two imagining what would have happened if we configured Blue Waters a little bit differently. So if we had taken all the nodes that we had and made them all XK nodes, and the system would be designed to be on the top of the top 500 list, right? So if we designed a system to be number 1 on the top 500 list, what would a Blue Waters look like? And then we'll go through see some of the science that may have been impacted by that decision. So the same coverage is what we're using. And if we look at the characteristics of the top 500 Blue Waters versus the sustained Blue Waters, you would see a much higher peak performance because all of that's coming from GPU space. You would see the ratio of the x86 performance flops to the GPU performance flops, not a factor of 9 there rather than a factor of about 60%. The number of nodes is the same, although the asterisk is there because it's not clear to me that we could afford as many nodes with the XK nodes. Even though they have less memory, they actually are more expensive than the XE nodes. But assuming that we could, or that our vendor would be cooperative and let us do this, this system would have a LINPACK number about 26.4 petaflops, far higher than the number 1 system that was listed on that list, and it would have been number 1 for several cycles at least, right? But still, the sustained performance based on our measure that represents our workload, or the best we can within a reasonable, practical, feasible amount of testing, would still be quite a bit below what Blue Waters is. And that's based on this ratio, how many projects can actually use GPUs, how many work well there. Another impact would be only about 60% or so of the memory, available memory capability, the aggregate amount of memory would be low, and again, that's based on the number of nodes there, and it would be unclear whether we could afford all the storage or not, so that's a TBD. So this is, if we were to design, if we had decided to say we want to be number 1 on that list, and that's our main criteria, because it's easy to explain to our stakeholder or our politicians or to a newspaper reporter that we're number 1 for at least a little bit of time this would have been the system that the science teams had to run on. So now let's look at some of the science and application activities that have been occurring recently. These are updated from that book. They're some of the same science teams. But one of our outstanding problems or challenges is to understand space weather. This has become very important in the science community and very important in our advanced electronic lives. So about a century and a quarter ago, there was a major solar event that just happened to occur when the Earth passed through that range that is measured to be beyond anything else observed since then. But there are estimates of what that would have done. It disrupted, for example, it burned telegraph wires. So on Earth, coming through the atmosphere, the aurora was down near the equator, but it actually burned up telegraph wires with the solar event, is what the documentation says. So what would that do today to our GPS system, to our cell phone systems, to our satellite observing constellations? It would be highly destructive, on the order of trillions of dollars of destruction, if we happen to have an event coming through and we don't have improved ways of protecting those devices. While this simulation was running on Blue Waters, or at least the team was working on Blue Waters, it turned out that there was another event on the sun, a solar flare event, that was observed with satellites and ground-based telescopes, and we missed that flux of radiation by about a week. So we were lucky, because if it had occurred slightly later, we would have been in that range of as all those particles come out, and we would have had at least a part of this impact that is being studied. So that's why this is a project that is very important. They are producing not just simulations at unprecedented scales that have to go from actually how the sun dynamics works at very high resolution to generate such flares, how the flare comes out, how the radiation transport, and then how it interacts with our magnetic sphere, and how it actually compresses and pushes on the magnetic sphere so that there's decoupling back here. So these two regions are what's being studied in terms of the primary and secondary reconnections, the bow shock, how that all is done at unprecedented abilities to do that, and all in one simulation project. So the times of scale, you can see, are quite dramatic. This is also one that is very I/O intensive, and doing this problem, that problem, similar problems, smaller problems, less precise problems have been done on other large systems like the systems at Berkeley, but the I/O capability of Blue Waters enabled this to be much larger scale and much longer event in duration, or simulated event in duration, than is possible on some of the other large-scale systems. So this is not only enabled by the amount of processing we have, but by the balanced I/O investments that we've made here. This now is being part of our release, I believe, in a couple months, in July, for our first dome show. Donna Cox, who's here with the Advanced Visualization Laboratory, has a grant to produce public documentaries of computational science and analysis. And the first one is on space weather, so they're using 3 or 4 of our teams. HOMA is one of the team members. There are several others that are studying similar type things of solar flares, solar events, and its impact on the magnetosphere. So Cadence is the name of that project. And the first, I guess, the premiere of that is going to be, I think, in late June for the first time. It'll be a 3-dimensional IMAX dome show, and then a variety of other products coming out of that. So that's kind of cool, and trying to get people to understand what this is. They did a premiere of that at our Parkland Community College, has a planetarium with a dome, and that's where they premiere the rough cuts and stuff. They did that a couple weeks ago. So here's another one. There's 2 of this way, Brian O'Shea. He is studying the evolution of the universe, right? So from the Big Bang through how did galaxies evolve, and then what does that mean? And those are the things that we're observing now, far redshifted in the distance, right? So these are the galaxies in the first million years of the universe, and now we observe them, and by understanding how they were created, we begin to understand what we're really observing. Brian's point was they now have gone from being able to only simulate 8 galaxies with this much physics to a region that contains over 1,000. So they're not doing the entire universe, they pick a region and narrow in on that. But before, the best they could do was 8 galaxies with this, now they can do 1,000. So now statistically, he's able to start to compare the types of galaxies that are formed and different shapes, different characteristics of the galaxies statistically rather than just anecdotally. So that's a major breakthrough for this group. I should have mentioned Home is providing all his data to people who design satellites and instrumentation. So that's the guidance for the best data set for quite a number of years that other people are starting to use. So not only do we write scientific papers, or the science teams do, but now, because they're so much further advanced than they were able to before, their data, just what they have come out of the simulations, now becomes valuable input to a whole range of other types of activities that go on. There's a whole bunch of reasons why understanding galaxies is important, particularly the search for dark matter and dark energy, and the fact that all galaxies have black holes at the center of them. But this is now a very important component that wasn't even recognized up until about a decade ago, of why it's very important to get to how these galaxies are created, what influenced them, and how they work. So that's another example. And they've increased in all dimensions, physics, fidelity, and time about 100 times in each dimension by being able to use blue waters. So that was phenomenal results. A different type of simulation, but in the same domain, is Di Matteo, who is studying the first quasars. But what she's done is she's taken the entire universe, the entire scope of the universe, evolved the universe as it's over the first, say, million years after the Big Bang, and is looking to figure out how galaxies and quasars, but she's done a much bigger space. She uses AMR, and they were able to make predictions. So this is the first time anybody has simulated even a section of the universe at the resolution of what our next space telescope will show. So the Hubble is getting near the end of life. The James Webb Telescope is scheduled to go fly in, I think, about 2 or 3 years. So now this data set, petabytes of data, is now available for the people who are designing the analysis pipeline for the James Webb Telescope to be able to use, because it's about the same resolution that next generation telescope is going to be able to see. So that's kind of cool. Plus it has the ability to draw its scientific insights in its own right. 1 trillion particles. It was all held in memory. It required the full system over weeks at a time, and used about 1.2 petabytes of memory while it was running. So this problem could not have even been considered without, again, the balance of the system that we have, and it's not just a floating point operations problem. So this could not have been done any other way. Here's the simulation previously, 300 square arc minutes, and now they have 200,000 star-forming galaxies that they've simulated and have that at resolutions. And here what they're trying to show is they actually have galaxies of different types of shapes and statistical properties. So for the first time, from first principles, how these galaxies formed and matching observed data is what's exciting about, or one of the things exciting about that. I mentioned that we observe a lot of things about the blue water system. This is an example, so 8 billion data points a day. Basically, every minute, every node, every NIC, everything on the system is queried about how the performance is going on. So these are 2 codes, 2 different simulations. Here, this is the one I just talked about, running almost full time, and showing this is the available memory left on the system down here, and some I/O activities. So we're showing almost all the memory is used by this code. This code uses less memory, but the other thing is this showing the what is this? Oh, this is the I'm sorry. This is the I/O of the codes, and this is the network communication of the codes. So while the system uses 1.2 petabytes of memory, it is not particularly communication intensive, but was followed by another code that is communication intensive. And actually in this code, just by observing remotely, and a lot of the work was how do we do this without perturbing performance, right, without introducing noise. You can see actually the time steps going on, and we can measure the time steps. We can actually measure how this code is performing, how consistently it is, by seeing these time steps that are natural in the code, right? These are synchronization points in the code, so we can observe that. We can observe what they're doing with I/O and how that influences what goes on over here. So this is an example of the amount of data and the ways that we're starting to use that data. Turbulence in stellar hydrodynamics. Again, something that was quite novel in terms of understanding how this works, and this is important because this is where our heavy elements come from. This ran over a petaflop on about 4,000 cores, and another neat aspect of this is, and we'll talk a little bit more about workflows, another neat aspect of this is the fact that this team was spending 15 days to be able to understand what they simulated. So they ran for a while, took them about 15 days to get the data to where they are. The total rendering time was 24 hours. They could do that much faster on Blue Waters, but that's what it takes on Blue Waters. And we were able to get that time down, from 15 days to 24 hours. So quite an improvement on how long it takes them to be able to understand what was going on with their system. My last example is the one about Seismic Studies in Los Angeles. This group is on their third campaign. Each time they do a campaign, they get higher resolution, higher frequencies of the shaking, and they're doing a 3D physics-based, which means from first principles based earthquake set of ruptures. They do about 5 of those in different locations, and rather than just using empirical standard data for their studies. This impact is on designing building codes, designing building. There's about 400 dams that produce hydroelectric power in California that need to be retrofitted. So their work is influencing which dams go first, things like that, and also disaster response. This is a combination, very large simulations that run for a relatively long period of time. At scale, a couple thousand nodes, but then they also have to run 100 million jobs. So we were able to take that time down from the order of 9 months to about 2 weeks to run the 100 million jobs by having them not have to move the data, not having to distribute what they're doing. So the workflows are very important, and the difference between their previous simulation abilities. Here you see the big red stripe, that's the San Andreas Fault. You see some green and a little bit of blue. But the difference is now with the much higher resolution, much better physics, they can see still the San Andreas Fault, but they realize here there's a great deal of potential for, this is the LA Basin, great deal of potential for destruction here. There's less potential over here. So they now have a much more accurate map of where different types of codes and where different types of things need to be applied, as well as disaster preparedness for this. I lied, but I'm going to go real fast over these. This is what happens when you have equipment flying in space, observing the Earth, and it's starting to slow down and decay, and we can't launch them as fast as they're falling out of the sky. So this project is a many variant optimization project to maximize the coverage we have on the Earth, to gain knowledge about our water resources for drought, for flood, other things, and this feeds into a whole variety of other impacts as well. And then the climate simulations, that are going on. This is actually the code that is designed to be the next US-based climate assessment, the UN climate assessment for the next IPCC. That's what this code is being developed for. They spent about a year because they got the high resolution done right that they want for this next generation, but they found out that they got weather events like hurricanes and hurricanes and severe weather, but they didn't get the amount of rainfall right. So there was a disconnect, and it turned out how they were parameterizing clouds was off for that resolution. So they had to spend a year about how to fix that. So now they're both aligned with observation. And then Klaus, Chilton's group, we have representatives here, both about, you've heard about the HIV capsid, and they can talk much more about that. But also, I think it's kind of neat that now, the first time, if I understand right, a full organelle in a cell was simulated for how photosynthesis is actually works at the atomic level, or in actually the electron level, if I understand right, for converting sunlight into chemical stored energy. So that's a first that came out this year as well. So in the last couple of minutes, I'd like to talk a little bit about some activities looking to the future. So one of those activities is we've held some workshops. Some of you attended, Todd attended, Rick attended, for what we call brainstorming high performance computing and data. And one of the motivations was that there's a National Academy report that NSF commissioned about what they should be doing in the future for computing. And they had some questions, and we wanted to get some community people together to provide input. And the other motivation is that all the NSF resources are, the major ones, are due to retire sometime in 2017 or 2018. So this is the time that there have to be plans for refreshing those resources, and NSF wants guidance on what that should be and how they should go about doing that. So we had two workshops. One was requirements and needs workshop. What are the science requirements? What are the needs? The other is alternatives to implement such a set of reinvestments, if you will. In this case, the workshop only was focused on the workshops on what we call the high-end advanced digital ecosystem, track 1, track 2 systems, leadership class networking, and a variety of other things, including workforce development and application software to use those systems. So it didn't try to address all of the cyber infrastructure needs. It tried to address the ones that were important. I'll mention one other activity that NCSA is heavily leading. John Towns is one of the principals, and that's what we call science-driven CI. So this is a little bit of a broader, longer-term definition of programs, maybe something that would last for 10 or 20 years, but would take a while to start up. But it also covers a broader breadth of what the cyber infrastructure is. So that's a website that you can go to and look at. There's a preliminary report and some meetings that we have going on. So one of the things, a couple of things that came out of these discussions. One is the flow of influence. In terms of what we're describing here is starting with best of breed or frontier calculations, best of breed methods, flowing down into out front, kind of more teams using that. So for example, the scale that NAMD works on, that did those two examples that Klaus and John and Jim work on, now are being used by other researchers to do similar sized problems. So that's a flow down from the first of a kind method down into others applying it, down into community methods, and then basically being embedded and almost ubiquitous. So we see this flow going on all the time. It's probably not unfamiliar to you all, but that's an important thing, that it's not just the first time something is done. This flow has to be supported throughout the community. The other flow that has to be supported that has always been there but has not been as tightly identified, and this comes from Tom Jordan, is the cycle of, you can start anywhere in the cycle, but let's say you start with some type of system model. You want to verify the system model, you simulate a lot, and then you go validate it with experimental real-world data. You get better data, then you simulate it, you form or modify your model, and this spiral, it gets faster and faster. And what we've seen across many of the science disciplines is now this is almost cannot be distinguished from when you're in this phase and when you're in that phase and when you're in this phase. It's almost simultaneous in what's going on with many of the teams. So that's a change that we have to accommodate in the future. Next generation challenges that we believe we've identified with the teams from working through several different workshops. I will say, and Mark left, so he might argue with me, but it's all the software. It's the software stupid, more or less. It's not the hardware that is the challenges for the future. And I'll tell you why. So there's going to be continued dramatic increases in fidelity. That could be numbers of atoms, that could be higher resolution spatially, could be all types of things there. It also is the number of ensembles, right? So I don't think that that's a good word because it has connotations of embarrassingly parallel. Now all these large-scale problems have to be run multiple times, not just for uncertainty quantification, but for example, in the seismic effort, they actually simulate full ruptures in the Earth in 5 different locations. Because they have to, because they don't know what's going to happen, right? So they get different parameters and how that impacts the shaking of buildings and stuff. So those are, people would call them ensembles, but it's not the same connotation we used to use. Longer simulated time periods, the space weather, that's about a 2.5 hour simulation. The event actually takes about a day and a half. So they would like to go to the full event to understand the implications rather than just 10% of the event. Same thing in a lot of molecular dynamics simulations. Many of the other simulations are still only able to study a relatively small part of the event time, and there's things that we don't know will happen with those longer time periods, right? Increasing number of problems. This is the idea of you can do 100 million atom simulation, and now you have probably 20 or 30 teams that are now wanting to do different problems at that same scale. Once you enable a certain scale, once you enable the software to run at that scale. So these are characteristics of our future. Changing workflow methods. We're finding out by working with these teams, be it Tom Jordan or be it genomics teams, some of the biology teams, some of the people from Mayo Clinic, that there's an awful lot of work in the workflows themselves, and they've grown up kind of holistically. There are many, many tools, many, many implementations, but much of the time, if you measure the time from the start of trying to solve a problem to the time you have insight, not just the computational time, much of that time, as I pointed out a couple times, is now limited by the workflow time of the entire problem. So there's many things in here. Visualization is one thing we used to think about, now analyzing that loop of validating and simply moving the data and understanding it, and having many small tools hooked together, maybe with files or maybe with pipes in workflows that used to be simple but now are trying to do something bigger. So this is one of our big areas, I think, that we have to concentrate in, not just on how do I scale up a parallel MPI job, but if we're really going to make and address the needs of research, industry, science, engineering to get to better solutions faster, we have to address this in a much more, organized way, as well as malleable and elastic resource management, either because of resiliency or because jobs want to grow and shrink and you want to use the resources well, and we need programming models for workflows as well. Increased integration of data sources, but also increased use of simulation data products. I mentioned a few of those. That didn't happen before. We were not producing big data except for what was consumed again by us. But we're producing now, or the science teams are, not us, we're helping them, are producing a great deal of data that's valuable for others to use. So we introduced a data sharing service on Blue Waters so people can share their data out to the world in a reasonable manner without having to give individual copies out to people. And that's petabytes of data, so it's things that can't be held elsewhere. You can't stick it on a little Dropbox or something like that. And then last but not least is changing algorithmic methods, driven in part because our architectures are changing. So more layers in the architectural hierarchy, near memory, far memory, different levels for storage, different processes for how CPUs work, more mini-core. So all those things drive algorithmic choices, but there's also, just for science and, and engineering improvements, I would say, at least at one point, I had studies that said almost half of the time the solution is improved by algorithmic changes in the science methods as it is by just the raw hardware. And I would submit that we probably, with the lack of great increase in clock speed, are going to rely more on the software algorithmic changes, the method changes, than we have in the past. And that's part of our program that we're introducing to the science teams now. So out of these workshops, and there were some others precursor to that, some of the conclusions, there's compelling evidence that computation data activities are now entwined inherently, that cannot be separated from all ranges of investigations for science, engineering, industrial work. The high-end computation and data computing resources are critical to discovery in all fields. There's great progress in expanding the use of high-performance computing that NSF has made. Lots of outreach, lots of getting more communities, and now they're starting to use things, including things like how disease is spread, contagion, agent-based computing, and big data computing. NSF is the primary agency responsible for basic science in the US. So they have to provide the resources for this. One estimate was about 50% of what is used on Exceed is non-NSF funded activities, NIH, other things. So that's important. They're supporting the entire community, not with limits, and in all ranges of endeavor. Other conclusions are, because of that, they need to have cycles of large-scale systems that and have benefits of multiple types of systems, but not too many. More, there's 2 to 4. You can argue about 2 to 4. 1 is not enough. 5 is too many, and that's what that comes from. But they have to have the size and capability to do the things that are at that frontier, at that best-of-breed edges or limits as well. Sustained funding, something that is planned on. Everybody asks, what are you going to do for Blue Waters next? At the moment, we can't say what it is because we don't know what the funding streams or goals are. So we're working on that, that we can talk offline on if you want to understand what we think might happen. But all those things are very important. One of the things in this is also the frontier science. These examples that I showed you that took a while for the software to develop that way. The teams worked on that even before the system was there. The frontier science is what's going to suffer first, because those science investigators, those postdocs, those grad students are going to go do something else. If they can't expect, I can do something novel, do something new, and have a resource that I can run on. So, so that's another one of our consensus conclusions. The funding for within the National Science Foundation. This is the government funding, and they put together reports with every budget of what they call high-end computing, infrastructure, and R&D across all the agencies. So looking at the NSF funding for this, you can see going back to almost 1998, it has been flat, with the exception of the stimulus bills that were done in 1999, right? So that's what that bump is. This is also the total increase in budget for all types of IT, advanced IT, again, from the same government report. So that's been going up in NSF, but the high-end computing and data activities have not. If we look at the DOE space to compare to, this is the total here, and the high-end computing and data space has tracked that very nicely and actually takes up a larger share of that. So there's different investment profiles, but for the purpose of this report, this is very problematic, right? So because more and more science, more and more teams are coming and wanting to do bigger things, they've been encouraged to implement much more efficient processes, and now the resources are being constrained, or basically highly over constrained in terms of what people can actually do. So starting to inhibit those with that. And here's another view just in terms of the percent of the total budgets of the two agencies. And even though NSF is about 20% bigger, clearly that's not the case in terms of their computing. A couple other items, large community-based repositories. NSF has a challenge because we all are being told we have to save our data, we have to have data that we use for publications promised there, and we have to be able to do that in a very reliable manner. But NSF and others and DOE too, worried about people just like closets, put all your stuff in a closet, forget about it, you don't go back to it until you're moving your house, right? So this is for community-based repositories necessary, a couple of the complicated workflows, things we've talked about, and investing in the software improvement and development in the workforce. And a part of the consensus was support of industry in a more effective economic model. So I'll go through the rest of those because I think I'm out of time. I had a couple brief examples of what might be done in next generation systems. So the main summary message, I think there's been tremendous progress on use of a resource that didn't exist 2 years ago that is far larger than any individual resource in the NSF academic portfolio. We support about $500 million of funded research. If you count the research money going to the teams that make use of Blue Waters. And we're trying to serve as a catalyst and a research tool for next generation systems. And we didn't talk about all the aspects of Blue Waters, just about the computing part of the aspect. So hopefully I talked a little bit about floating point operations. I talked a little bit about what we've been doing with Blue Waters, and you're up to date. But I'd be happy to talk now and during the rest of the conference. Thank you.